Well, that will go. Okay, thank you. Okay, you have. Oh my God. Okay.
Welcome back. So our next speaker is Panayotis Kevrekidis, Nonlinear Waves in Granular Crystals, Modeling, Analysis, Computations, and Experiment.
Thank you very much, Karima. Thank you all for coming. It's a pleasure to be here. Thanks to the organizers for giving me the opportunity. As I usually say, I'll talk about joint work with a number of good friends and collaborators. Whatever good you've seen here should be attributed to them. Whatever bad should be blamed on me. We've done a number of things over the years on this subject. I just want to mention a review and a sort of gentle introduction in a short book for anyone that may be interested in the subject. So what do I want to talk to you about today? I want to tell you about three themes. One is shock waves, about which I know the least, and I'll tell you the least, but at least it will connect me to the theme of the workshop a little bit. I'll talk to you about traveling waves and then about discrete breathers. I'll mostly talk about homogeneous media, but maybe a touch at the end about heterogeneous media, and I don't think I will have time for anything else than just some conclusions. Okay, so granular crystals, what are they? We haven't heard anything related in this meeting. These are just chains of beads which are interacting elastically with each other. The beads can be vertical, like so, or horizontal, like so, and for everything today, they're going to be horizontal. Now, these beads, basically, you compress them, and then a wave, because of their elastic interaction, kind of propagates down through the chain. But this is a very interesting medium for a couple of reasons. One of them is you can have different kinds of beads, or you can have the same beads. That is, you can be very homogeneous, or you can be very heterogeneous or disordered in this media. So this media can go all the way from homogeneous to disordered. Another kind of advantage is you can actually probe the beams. In the old days, you could probe them through piezo sensors. These days, you do much more contactless, if you will, experiments where you scope with a laser Doppler vibrometer the first bead, and you measure its velocity as a function of time. Then you repeat the experiment, you scope the second bead, and you measure its velocity as a function of time. You can really do it for all beams, and so you can have a distributed view of the field of this experiment in space and time. So two of the major advantages of these lattices is they can be homogeneous or heterogeneous, and you can really visualize the experiments in space-time. All right, what are they good for? Engineers actually use them for practical applications. Multiple ones of them they try to do with acoustics, the same things as we do with optics. I just wanted to highlight here one example of what Chiara D'Araio and J.K. Young do in their lab. They used to do it at Caltech. They have sort of a sensor where they send the kind of traveling wave that I will talk to you about in a little bit, and they sort of scatter it off of a bone, and depending on whether the bone is healthy or osteoporotic, they have a different response. They can measure that response, and based on that, they can assess the risk that your bone has for fracture. So this is kind of a practical application of these as sensors. But of course, this is a math conference, so I really want to tell you about what the math is. Actually, Alejandro, I didn't think there was going to be an FPUT kind of mention, but Alejandro did have it, although he didn't really talk about it much. Mass times acceleration is a kind of Newton dynamics here, is the force that each of the particles feels from the particle to the left, and the force that each of the particle feels from the particle to the right. This is an elastic force, a compression force between the beads. And Heinrich Hertz in 1882 showed that this force is proportional to that relative displacement, to a geometric power. That power P, for our practical purposes, for spheres, which I'm going to consider for the most part, is going to be 3/2. So it's a non-linear system just because of that kind of elastic interaction. There is a prefactor in that interaction that depends on elasticity and geometry. I'm not going to worry about that. Think of it as just a constant. But what is much more important, and that's the third big advantage of these chains, is this delta naught over here, which is called precompressional displacement or precompression. What is that? Before you do the experiment that you're interested in, you can actually compress the lattice that you play with to begin with. And if you compress it, you create a displacement between the centers of the beads of delta naught. Now, the reason why this is important for us is because now you can think of different regimes. You can think of regimes where the centers of the beads have a displacement which is much smaller than delta naught, and then you can Taylor expand, and you can think of keeping the quadratic and cubic terms for an alpha or beta FPU type lattice. Or you can go to the opposite end, and you can scrap this delta naught, you can make it 0, and then you have a purely nonlinear system, a system that does not have linear dispersion. So I talked to you about two advantages already, homogeneous versus heterogeneous. I talked to you about the the fact that we can really measure these things in space-time. A third advantage is you can make this weakly nonlinear, this being much smaller than that, or you can make it purely nonlinear, where this delta naught is absent. So these are three of the major advantages of these kinds of lattices. As I told you, I'm going to look at p is equal to 3/2. For the most part, this is the system when you have all the chains being the same. This is the simplest variation, if you will, when you have a dimer, big bead, small bead, big bead, small bead, big bead, small bead, then the ratio of the masses becomes an additional parameter in the system. So that's my playground. These are my equations, okay? Okay, so what can we do with them? Well, the first thing that I will do is I will make them look like a wave equation by looking at this relative displacement, the strain, as we call it. And in this relative displacement, the equation looks like this. This is familiar to us. So acceleration is something like a second derivative, well, like a 3-point stencil, really, in space, okay? So it looks like a wave equation. But I'll tell you that it has some differences from a wave equation. Anyway, just pursuing that, I'm going to start with a blob, and I'm going to let that blob, just as we teach our undergraduates via D'Alembert solutions, to split into two blobs that propagate left and right? Looks very nice, like nice waves. But remember, there are differences between this and an actual wave equation. Two differences in particular that are going to be important. First of all, this is discrete. It is not continuous. That's going to come into play in just a little bit. Secondly, and most importantly, this is nonlinear. This is not p is equal to 1. It's p is equal to 3/2. What does that do? This starts these sort of pulses that propagate and starts steepening them. And eventually it breaks them, justifying my presence in this conference. It creates some sort of dispersive shock wave, okay? So the nonlinearity of these kind of shows through that. So what can we tell about these shocks? First of all, we kind of like continuum systems in some ways better than we like discrete because there are chain rules and all that stuff. So how can we make this into a continuum system? We look at long scales. We can multiply by an epsilon square here and an epsilon square there and look at slow time scales of epsilon t and try to take epsilon to 0 so that we can make this into a derivative. And lo and behold, you get this kind of partial differential equation. It looks like a nonlinear wave equation. You can actually prove that the solutions of this equation in slow space, slow time, approach the lattice solutions up to controllable correction. So you can actually prove that. And what kind of PDE is this? It's actually a P system. So people in hyperbolic PDEs kind of know about this, which means that it has eigenvalues or characteristic eigenvalues that scale with the amplitude. What does that practically mean? That means that if you have a big amplitude, its speed scales with the amplitude to a positive power, which means a big amplitude travels fast, a small amplitude travels slow. So the big amplitude is going to overtake the small amplitude and therefore steepen and eventually make the thing shock, okay? So that's how we know that there is going to be a shock in this kind of structure. But can we say something more about the shock and be quantitative about it? And so we know that this is a wave equation, but we know it has transport left and right. So we can actually find the first order nonlinear transport, if you will, generalized Burger's equations that are compatible with this second order equation. If you do that, you can actually solve these equations. You can find this explicitly. And then, of course, these are first order nonlinear transport equations that you can solve formally via characteristics. More importantly, we know that the characteristic that propagates slowly and the one that propagates fastly will actually intersect. And when they intersect, they will form that shock. And indeed, if we try to take these two characteristics and make them touch each other at space-time, we can find the time at which this shock will form. And this is a well-known result in this kind of systems, that the time at which things will shock will depend on the decreasing part of your initial data, and in particular on the slope that you have at the inflection point. If you measure that slope and then find the opposite inverse of that, that will give you the time at which the first shock will actually form. So we can actually measure that. Here is my pulse. It will start steepening. It will steepen some more. And eventually, it will form this kind of Hamiltonian shock. And I can measure the time at which this will break and then plot this time here. It's the one time that I actually do things as a function of the exponent p. You can plot that time as a function of exponent. Remember, the experiment is at p is equal to 3/2. I plotted this as a function of p so that you can see that at p is equal to 1, this time of shock diverges. Why does it diverge? Because p is equal to 1 is linear and does not have a shock. Okay, but you can measure this time for other occurrences of p, and you can find good agreement with the actual numerics. And so that's kind of the time at which things are going to shock. Just to give you a sense of the time scale of these things, of the history, if you will, of these things. These kinds of things have been studied in FPU systems since the 90s, if not earlier. Here's an example from the work of Stefano Ruffo, Poggi, and Kantz in 1995, where they were trying to use these characteristic solutions, the PDE solutions, to describe the discrete system. This is just at the breaking time. This is a little bit after the breaking time, and so on. You can see how the continuum matches the discrete. And they actually even measured the difference between continuum and discrete. And you can see you do a very good job with the continuum all the way almost up to the breaking time. Then you kind of lose it. The error between continuum and discrete grows as you approach the breaking time. So this is what was done in the olden days. In the modern times, this is something which is very recent, the group of Tal Cohen at MIT. They do experiments with, and this is a different experiment, with magnets. Okay, so these are magnets, and they actually kick the magnet at the end, and that produces a beautiful shock wave kind of propagating down through the chain. They also have space-time resolution. You can actually see your shock, okay? You can be shocked by it. And then they can actually measure the second bead and the 8th bead and compare the FPUT, if you will, description of it in dotted and the experimental description in solid. And that's the kind of agreement that they have about the velocity of these beads. So that gives you a sense of how far along we've come in describing those shocks. I think this is a great time to study dispersive shock waves in this system. And with that, I'll just say that we are looking at that in these discrete systems right now. We've been thinking about the Riemann problem with Michael Herrmann and Chris Chong, who gave a talk about this in this semester, and Mark Hofer and Pat Sprenger are helping us with that recently. And so we have been looking at sort of along characteristic lines of this discrete system and have been trying to realize a sort of phase portrait of the system that has kind of the nice homoclinic over here and has sort of the near linear waves, so the front and the tail that we heard about also from Gennady and others, that to say that even the discrete systems can actually have Riemann invariance and can be described by similar ideas and so on. I refer you to Chris's talk about details on that. I really want to move on to my next item, which is the traveling waves. So traveling waves is the workhorse of these granular systems, the sort of thing that has been studied for 40 years since Vitali Nestorenko in the 80s. And that's the sort of thing that will happen if you kick the chain on one end and see what propagates down through it. These are realistic numbers, although this is a numerical simulation, not an experiment. I'll show you an experiment in just a second. And you see a beautiful propagation of a traveling wave over millisecond timescales. The lattices are of the order of tens of beads in this system. Here's the experiment. I promised it. And this is the experiment, the group of J.K. Young at Washington. Velocity as a function of space and time. You see a beautiful propagation in experiment. Space-time probed somehow, a traveling wave over through the chain. Here is the traveling wave in simulation and the traveling wave in experiment. And the only reason I know how to distinguish between the two is this is a perfect traveling wave. In the experiment, almost a perfect traveling wave, but still as good as it gets. What is it that you're seeing? You're seeing the wave pass through bead 15, then that bead gets excited, then the wave arrives at bead 16, then that bead gets excited, and so on and so forth. So this is the wave arriving at different beads of the lattice. All right, but then how do we study those traveling waves? Well, we do the sort of thing that we like to do in dynamical systems. We go to the co-traveling frame. But then it gets to be a little bit of a nightmare. Why? Because we have a time derivative on the left that will give you derivative over here, and we have discreteness on the right that will give you advanced delay equation. So you get a nasty beast, which is differential advanced delay equations. How do you deal with that? In this particular case, to the rescue comes Bob Pego and some of his students, which basically said you can actually Fourier transform this. If you Fourier transform, every time you have a derivative, you bring down a factor of I times k. So two derivatives means a factor of minus k squared. On the right, if you Fourier transform, this gives you an e to the ik. This gives you an e to the minus ik minus 2. For those of you that like lattices, this is the lattice dispersion relation minus 4 sine square of k over 2. So you divide this by the k square, and you get this equation. And what is this equation? If you think about it, this is nothing but a fixed point iteration. Let's do it for delta not equal to 0. You give me a phi, I raise it to the pth power, I Fourier transform, multiply by this sinc square function, and I get myself another phi. And I keep iterating this until I actually converge. And if I converge, there's no approximation here. By construction, I get myself a traveling wave of the original system. So I can actually construct traveling waves by this nice little iteration tool. And if you don't like Fourier transforms, don't worry about it. You can always go back to real space. You can Fourier transform back, phi hat hat, the inverse Fourier transform gives you phi. The inverse Fourier transform of a product will give you a convolution, and it's a convolution of the inverse Fourier transform of phi to the p hat, which is just phi to the p, and the inverse Fourier transform of the sinc square function is a nice and continuous function, which is called the tent function, and I've represented it for you over here. Okay, so you just take phi to the p, convolve it with this tent function, and you get yourself a new phi. You iterate this to convergence, and you got yourself a traveling wave. Not only that, but you can also infer information about how this traveling wave actually decays. How can you do that? Let's take phi of x plus 1. You go one step to the right. And then you basically have this kind of formula. And you realize that this argument over here goes from -1 to 1, because the tent function is non-zero between -1 and 1, which means x plus 1 minus 1 is x plus 1 minus -1 is x plus 2. So this goes between x and x plus 2. But if you're looking at a decaying pulse between x and x plus 2, the largest value is at x. Therefore, you can make this less or equal to phi to the p of x times the integral of lambda, something that even I can do, or even my daughters can do, and it actually turns out to be 1. So that means that phi of x plus 1 is less than phi of x to the pth power. What does that mean if you iterate it? If you iterate it n times, phi of x plus n is less than phi of x to the p to the n. What does that mean? That's not your garden variety exponentially decaying pulse. This is a pulse that decays doubly exponentially fast. Okay, so it's a nearly compact kind of solution. On the other hand, I did this all without the delta naught. If you do put the delta naught, the precompression, you actually get exponential decay. So these pulses, if you do not have precompression, they decay extremely rapidly. In a semi-log plot, they decay still very rapidly, whereas the ones with precompression, they actually decay exponentially. So this is the exponential versus doubly exponentially decaying pulse. I talked to you about iterating this numerical scheme. Here's the result of this iteration, the exact, numerically exact traveling wave, the one that you saw in the experiment. And indeed, if I actually let it run for time 30, it arrives at position 30. This was a pulse that was prescribed to have speed 1. It's a perfect traveling wave, as it should, as it was prescribed to be. So this is my traveling waves. Of course, I need to pay some tribute, by the way, also to the KDV. So if you actually do things with precompression, you can actually look at very long time scales, 1 over epsilon cubed, very long space scales, 1 over epsilon, and then you can approximate things by the solution of a KDV. You can actually prove a theorem about that. Not only that, but you can practically use the KDV solutions in dashed line here to describe the tall and thin and fast overtaking the short and fat and slow, the collision of two solitons, and so on and so forth. So you can play KDV games, but this is only if you do have precompression. Okay? Finally, I want to pay some tribute to the NLS. Okay, people know that this is my favorite kind of object. As we talked about, sort of the carrier with some wave number k0 with some frequency omega modulated by a slow envelope over a spatial scale of 1 over epsilon, over a temporal scale of 1 over epsilon square. That dispersive scaling is going to land you to NLS land. Okay? What kinds of NLS solutions, though, do we actually get? So let's look at that for just a second, because it's actually quite interesting. You have to believe me that the NLS that you get is actually a defocusing NLS. And in particular, usually we look here at the edge of the Brillouin zone, because this is a lattice, so we look at k0 equal to pi. So if you look at e to the I pi n, that's -1 to the n. So this is something alternating up and down, up and down, up and down. You have a breathing, and the breathing is e to the I omega t plus complex conjugate. That's a cosine. So this is breathing. It's alternating, but also breathing up and down. And finally, as I said, it's a defocusing NLS at the edge of the Brillouin zone. Therefore, it has dark solitons. Okay? So the solutions that you get is a bizarre entity like this. That is, it is an entity that alternates up and down, the -1 to the n, that breathes also up and down, the cosine omega t, but is modulated by the slow envelope of the tangent, of the dark soliton. So it's a bizarre entity like this. How on earth am I going to create something like this in the experiment? In particular, because I was careful enough to tell you all the advantages of my lattices, I hid from you so far the disadvantage. So the advantages were homogeneous versus heterogeneous, distributed probing of the field, weakly nonlinear versus strongly nonlinear. But the thing is, those beads in the middle, I cannot address them. I cannot do initial conditions at will in these lattices. I can play with the boundaries, but I cannot address those beads in the middle. I cannot prescribe initial conditions. So how on earth am I going to create something as bizarre as this? The solution that we came up with was to actually send two pulses in from the boundaries, but in antiphase with each other. So you let the thing breathe, and you send it in antiphase so that there is distractive interference of the pulses that get in the middle. You get distractive interference right around the middle. You get things to breathe at the right frequency. You create the distractive interference. And the experiment, this is space-time evolution of the experiment, will get you this bright, this dark, so discrete breather. Okay? Not only can you get it in experiment, but if you follow the same protocol in numerical simulation, you will also get that dark discrete breather in numerical simulation. And if you look for an exact periodic orbit, you will get the solution as an exact periodic orbit, as a dark discrete breather. And then we said to ourselves, okay, we can do this for one frequency. Why not do it for many frequencies? We have knobs. Let's use them. And the experiment is the dark dots over here. They follow the branch of solutions. But then the experimentalists told us, you know what? After a certain point, we fall to something else. And then after a certain point, we fall to something yet else. And so then we asked ourselves, how is that going on? And we sort of did the continuation and found this snaking type bifurcation diagram in the system. And then the question is, what are these other things there? And I think this community will appreciate it. They are sort of the Canoidal Waves generalization of this dark breather. That is, if you tune and go to the second branch, you will have a triple dark breather as opposed to a single dark breather. In experiment, in numerical simulations that follow the protocol of the experiment, and even as an exact periodic orbit. If you go to the next branch, you will get a quintuple breather, the next kind of canoidal. You will get it in the experiment. You will get the numerical simulation that follows the protocol of the experiment. You will even get it as an exact periodic solution. And you can even go to 7. Okay? So all of these you can actually obtain in experiments and in numerical simulations that follow the experiments. And not only that, you even have more knobs than that. You can actually play with the amplitude of the drive. So far I was playing with the frequency of the drive. If you play with the amplitude of the drive, you will see that you have a stable triple breather branch. You can actually drop or fall up to a single breather branch, but then you can fall back down to a triple breather branch as you switch the amplitude around. That is, you have the canonical hallmarks of nonlinear dynamical systems. You have multi-stability, and you can have hysteresis in these kinds of systems. And you can probe things like that, triple breather to single breather, in experiments. Okay? All right, I don't think I have enough time to tell you about heterogeneous systems. I told you about 3 things about homogeneous systems: traveling waves, shock waves, and breathers. Let me just say a word about how heterogeneity can be dramatically different than homogeneous system for traveling waves. So remember, I did this beautiful, J.K. Young did this beautiful traveling experiment where he saw this kind of traveling wave. Now, Alex Vakakis, 10 years ago, decided to do the following thing. He said, okay, now I change my homogeneous chain, and I go from large bead, large bead, large bead, and so on, to large bead, small bead, large bead, small bead, and so on. And he did this experiment as a function of the ratio of the masses of the 2 beads. And what he realized is if you actually tune from the monomer, which here is like epsilon is equal to 1, all mass is the same, to the second mass being 6/10, 60% of the first mass, here's what will happen. Instead of propagating the entire energy of the system to the right, you will propagate less than 30% of the energy to the right. That is, the thing that used to be a beautiful traveling wave will now completely degrade if you go to 60% in the second mass. How is that happening in the experiment? Here's the experiment, the big bead and the small bead, big bead simulation, small bead simulation. You see what is happening. This is allowing radiation to flow away from the pulse. It is destroying, that radiation is destroying the original traveling wave. You see this in the big beads, and you see it even more in the small beads. And indeed, here's the experimental observation of the complete destruction of that traveling wave. The thing used to propagate. Now it allows radiation to go away. In fact, it interferes at the end of the domain after the sort of being reflected from the boundary, interferes with its own radiation to its own detriment. So the thing that used to be a beautiful traveling wave before gets completely destroyed as soon as you go to the heterogeneous medium. But then there are more surprises. If you go to a sort of isolated quantum of a value at a particular value of the ratio of the masses, which is this 0.3428, this magical value, what will happen is the big bead will oscillate once, will pass the energy to the little bead will oscillate twice and pass the energy to the next big bead. And that will pass the energy to the next little bead that will oscillate twice, and so on and so forth. And you restore a perfect traveling wave, but only for this isolated value of the parameters. Both in the experiment, this experimental results, this is a numerical simulation, and here is the sort of full glory of the experimental visualization in space-time of the restoration of a beautiful traveling wave, but only for this isolated value. Okay? You go further down, and there is one more of these so-called anti-resonances, another quantum somehow, another isolated value, 0.1548. The big bead oscillates once, the little bead oscillates thrice, and passes the energy to the next big bead, and so on and so forth. Again, in experiment, any numerical simulation, you get a beautiful traveling wave being visualized in the system, okay? So I don't think I have more time to tell you about lots of details of what we've done, but let me just summarize what I just told you. Let me just tell you what I just told you. I told you that these are systems that have a lot of flexibility, a lot of ability to produce traveling waves and other kinds of structures. That is, these are systems that can be homogeneous or heterogeneous. They can be weakly nonlinear or strongly nonlinear. And importantly, these are systems we can visualize in space-time. They have three large classes of coherent structures. One is the shock waves, for which I want to advocate, especially to this community, discrete systems, dispersive shock waves. It's really something to study. I showed you an experiment where they can really be visualized. I think it's something up and coming. Please consider it. They have traveling waves. It's a workhorse that has been sort of utilized for over 40 years. We understand it. We visualize it quite well for these single component systems. However, already there are surprises when you go to heterogeneity. And there are these bizarre dark breathers. There are also bright breathers, I can promise you that, in the heterogeneous media. So these have a lot of these coherent structures. But there is a lot still to be done. I already advocated about the shock waves. This is one big thing. These things are used in engineering, both for protectors, granular protectors, and to optimize transmission. So there's a lot of acoustic things that are being done with these things. So I definitely think that these are worth studying. Higher dimensional things are also worth studying. Experiments in 2D and hexagonal lattices have been done, but they are really at their infancy. And I think that this is a very open field. And if any one of you has thoughts or interests or ideas with that, I would be delighted to hear them. With that, I'll thank you very much for your attention. Thank you.
Thank you, Panos. Questions?
Thanks a lot, Panos. That was great. The discreteness of the system, you use primarily long wave approximations.
Yes.
To describe, say, the traveling waves. What are the limitations on speed and how narrow these traveling waves can be in this discrete system?
So, okay, so this is an important point because actually, especially in the absence of precompression, so there are two cases, and you mentioned correctly that I use the long wave limit, the long wavelength limit, especially when I derive KDV type things. So then I'm really looking at sort of long waves. But in the case without precompression, the case where I set this delta naught to 0, actually I am not using in any way the long wavelength limit. I'm really doing exact computations. And the reason is people have done long wavelength things, but they are not accurate. They are kind of ad hoc because there is no natural length scale to use there. And the waves turn out to be very compact, like within 10 sites they decay to 10 to the minus a lot. So really these are like 5-site waves, more or less. So long wavelength approximations are not quite the right thing to do. Although people for at least 3 decades were using that kind of approximation, it was completely ad hoc. And even when it actually worked, you could not really justify that it worked. So you really have to sort of address them with different kinds of methods, like these methods that really do not hinge on the long wavelength aspect. When you do have precompression, then you can really utilize that. There is a linear limit. There is sort of a long wavelength that you can, a kind of game that you can play, and you can even justify it from a rigorous perspective. But going back to your question, these are very narrow waves. They are nearly compact. So actually this brings up the question of studying compactly supported structures and what these become in the case of lattices and so on. This is one of the best known examples of nearly compact structures. So it brings up all of these questions. And again, you really have to play the long wavelength game when it's appropriate, and you really have to be discrete and respectful of discreteness when you have situations like this.
Okay, thank you. So I have a remark in the question. So first remark is the following. I have impression that this science starts in 95, but indeed it was done before by Vitali Nestorenko in the early 80s.
Absolutely.
And Vitali Nestorenko was a PhD advisor of Chiara Daraya.
Yes.
Okay, you mentioned her, so you should mention. And the most important result of Vitali Nestorenko, he was experimentalist, and he also worked on heterogeneous chains of beats, okay? Not the person you mentioned. And the most important results of Vitali Nestorenko was he obtained compact tones, okay, and the length of the solid tone compact tone was 5 diameters of particles. So now questions, okay. What is the length of, do you have compact tones in the case when you have precompression, delta naught is different from 0, or you have always exponential decrease?
Okay. First of all, I want to thank you for the comment and give me an opportunity to say a bit more. In a 30-minute talk, there is not enough time to say all these things. So Nestorenko has been the pioneer, especially of the traveling wave aspects of the system. He was actually the first one that did experiments in 1980s, papers in 84, 85, and so on. A book in the early 2000s. He has been the father of this area. So it's very good to set the stage on that. The compacton aspect. One has to be careful. I think this is something that they've been trying to convince this community for a long time. These are not truly compactons. Nestorenko always believed and wrote equations at the long wavelength limit of these being compactons. They are not really compact. They decay, and we can prove this with a doubly exponential kind of rate. Sorry, I'm going the wrong direction. But we can actually prove that they are not compact. They really decay with this doubly exponential law. So they are not truly compact. They will decay so fast that they will look to you compact, but they are not truly compact. Going back to your second question, in the case where there is precompression, then you can really see the exponential tail as a function of the precompression. Moreover, using this kind of formulation, you can prove that they have exponential decay. So this kind of closes the door on, in the case where things have exponential decay, and the case where things are looking as if they are compact, but they are not really compact. Okay.
Thank you, Panos. I also have a question, but I will ask you later.
All
okay,
right.
We need to move on. Thank you.
Thank you.
So our next speaker is online, and I already can see Zhang there. Zhang, hello, can you hear me? Hello, yeah, good to see you. Welcome. Yeah, so I believe we will see your slides soon. Can you share your screen, please? Yeah. Okay, so while you are getting ready, let me say, Zan, could you make